So we have a definition for displacement, which is the vector difference between 2 points. We have a definition for velocity, which is the vector change in position as a function of time. The acceleration just sort of goes to the next step. And we can define it as, of course, it's a vector, because we like vectors. That shows the direction and rate of change of the velocity. All right, so it's just the rate of change of the velocity. So if we wrote that in equation form, we'd write something like acceleration, which gets the little a symbol, is equal to delta v over delta t, the change in velocity over the change in time. All right. Now let me ask you this: does this look like an instantaneous acceleration or an average acceleration? All right. It's an average. So if we think a little bit, it's an average. Why? Because, well, if we remember average velocity from yesterday, it had the delta t on the bottom. All right. So this is the average acceleration. Units for acceleration. So the units of acceleration, you can read them off from the equation. Right? Velocity is in meters per second. Time is in seconds. So the units of acceleration are a meter per second per second. All right? I say it like that to begin with because that should give you a little bit of insight into what acceleration really is. What acceleration is it tells you how fast the velocity, which is measured in meters per second, is changing. So if you're accelerating at 1 meter per second, that means for every second that you're moving, your velocity increases by 1 meter per second. Okay, so that's how you should think about that. And that'll become maybe a little bit more clear as we do some examples. Now, meter per second is usually written as meter per second squared, just because it's easier to say. So that's our unit for acceleration. All right, now, of course, there are 2 types of acceleration, just like there are 2 types of velocity that we're going to deal with. Yesterday, you saw an average velocity and instantaneous velocity, so we, of course, have an average velocity and average acceleration and an instantaneous acceleration. How do you think I should write the instantaneous acceleration?
The limit is delta t goes to 0 of that expression.
Okay, that's the way to write it in all its glory. So the limit is delta t goes to 0 of the change in velocity over time. And of course, that is equal to the derivative of velocity with respect to time. All right, so a is equal to dv dt. All right, so that's our basic definition of acceleration. Let's just do a really quick, straightforward example just to work with acceleration before we move on to kinematics equations. All right, so we'll have a car accelerating. So I'm gonna throw in some random capitalization there. Has anybody read the book Paper Towns? No? Okay. Then it's a good book. John Green, great author. I highly recommend it. What? Paper Towns? Oh, you read Paper Towns? There's a character in there that likes random capitalization. Maybe not like this, but John Green is one of my favorite authors. All right, so a certain black Mazda 3, I don't know why I tell you what color and make my car is, because then you could probably go like damage it or something. When you get your first exam back, I'll show him. All right, so the Mazda 3 goes from 0 to 60 in about 8 seconds. So I want to figure out what is the average acceleration. Now, of course, we work in SI units in this class, so when I say what is the average acceleration, I actually want to know what's the average acceleration in meters per second squared. because miles per hour per second, or whatever unit that could possibly be, just doesn't seem like it's going to work for us. So I want to figure out the average acceleration in some other unit system, so I'm going to convert my velocities to meters per second. Now, of course, 0 miles per hour is still 0 meters per second, so that one's easy enough. So I just have to worry about that 60. But before I do that, I sort of want to outline how I like to solve problems in general. I'm sort of trying to give you every day a little bit more of insight in how I sort of think that you should approach solving problems. So yesterday we were talking a little bit about coordinate systems, drawing pictures, the basics. Whenever I solve problems, in addition to setting up a coordinate system, so we could do that here, we're dealing with 1D problems, so the coordinate system isn't all that tricky. I'll define this as the positive x direction. The next step that I usually like to do, draw a picture. Okay, fine. Also, very simple picture here. Oh, it's a funny looking car. Going this way and starts from here to here, and then the car ends up down here, doing 60 miles an hour. I guess that they start at 0. The car starts at 0, so we can get rid of that arrow. Okay, simple picture, nothing really terribly exciting going on there. But maybe most importantly is actually listing things that you know and you don't know. All right, I always like to make a list. Now, in 1D kinematics problems, there's only so many unknowns that you can have. All right, but as we get into 2D problems and we start to expand our horizons with what we're covering in physics, you start to get a lot of stuff that you're dealing with, and it makes sense to make lists so that you could, keep track of things. So it's a good habit to get into right away. So I just like to sort of go down the list and list out things that I may or may not know. In this problem, we're not really dealing with positions. I can write x as my final position, my initial position. I could write that down, but we're not really dealing with those. That's okay. I can write down an initial speed. I know that's 0 here. I know a final speed is 60 miles per hour, which I'm going to convert in just a second. I could look for the acceleration. That's exactly what I want to know about. And then I can know something about time, which of course is 8 seconds. Okay? So here's a nice list of things that I know and I don't know. And I can add, we're not dealing with positions here, but it's worth noting that I can do something about one of these positions. A coordinate system is always yours to choose. You always get to choose which coordinate system you want to use, which means I get to choose both the direction of the coordinate system and the origin. So in my picture here, it sort of makes sense to make, like the starting position 0. I get to pick that. So if I were doing something with a position or a displacement, then I am free to choose one of those. So I'm going to choose x naught to be 0. All right? But this is a good habit to get into right from the start because it will make life easier as we go forward. Believe you me. All right, so the first thing I need to do is convert my 60 miles per hour to SI units. So let's do a quick conversion. 60 mph. Does anybody roughly know off the top of their head how miles per hour converts to meters per second? 100 kilometers per hour. Yes, that's right. That's pretty exact. If you can just remember a factor of 2, that's also pretty useful. All right. So 60 miles per hour is certainly more than half of 100 kilometers per hour. But I always think it, just rough order of magnitude, a factor of 50%, a factor of 1/2 is about what it is. But let's do the calculation really quick, just because we can. So miles per hour, let's convert that to meters per second. We have hour on the denominator, so we want 1 hour, and that's 3,600 seconds. And then how many meters in a mile? 1609 divided by 1 mile. All right, so 1609 divided by 3,600, it's about 1/2, give or take. So that's where that factor of 1/2 comes from. But if you actually do that calculation, you'll see it's 26.8 meters per second. Okay, so like I said, if you're ballparking it and you don't feel like doing the calculation, not on my exams, mind you, but in general, factor of 1/2 is pretty close. All right, so we have the correct units now. We can figure out the average acceleration. Well, we know that our definition for average acceleration is equal to the change in the velocity divided by some time interval. So what we're looking at here is the final velocity minus the initial velocity divided by delta t, which is 8 seconds. All right, so I can plug in my numbers now. My final velocity I just solved for, 26.8 meters per second. Initial velocity is 0. Delta t is 8.0 seconds. And if you solve that, you get 3.35 meters per second squared. Meters per second on the numerator, another seconds in the denominator, meters per second squared. All right, acceleration's a vector. What's the direction of my acceleration? All right, good. It's in the positive x direction or to the right, whatever you want to, however you want to label that. Right? You've got to make sure to include the direction if it's a vector. All right. Any questions about acceleration yet? So far, so good? Va bene. All right, so I want to focus a little bit more on that direction thing, though. Let's talk a little bit about the direction of acceleration. Let's do this in the form of a picture. So imagine then, in this previous problem we had something like this. We had a car that started at rest and then started to accelerate. So a little bit later, it was moving, kind of slowish. A little bit later, the car sped up, moving it a bit faster. And then a little bit later yet, the car is really cruising now. All right, so this is sort of a picture of a car that's accelerating. It starts at a velocity of 0, but it has some acceleration. So the velocity increases, it increases more, it increases more. Okay, this car is accelerating. Right? We would say that this car is accelerating. All right, no big surprise there. Well, let's flip that picture around now and let's look at the car which is going very, very fast at the beginning and then is slowing down a bit. So a little bit later it's going yay fast. A little bit later it's going this fast, and then eventually it comes to a stop. Would you say that this car is accelerating? You would. All right. I would agree. But I think that a lot of people would say that this car is decelerating. In physics, there's no such thing as deceleration. Okay, we don't talk about deceleration. All right? Anytime an object has its velocity changing, it is accelerating. Now, of course, this car, the top car is speeding up, the bottom car is slowing down. I don't disagree with you there. And so that's what we think of deceleration. But when we think about deceleration, what we're really referring to is speed, a change in speed. Okay? Now, why is it important to point out a difference? The reason that it's important is because if I kept going with this car, I kept drawing a picture. Actually, this is kind of weird because I'm going to make it turn around. So now we're going to keep going with the car, and it's still sort of accelerating at the same rate, but now it's going to go back the other way, like so. As this car went from moving very, very fast to stopping and then going backwards, the actual value for the acceleration, if I drew the arrows the right size, didn't change. All right? The rate of acceleration, the acceleration, the magnitude of the acceleration never changed value. Okay? Even though it stopped, the acceleration was a constant value for that car. Okay? And that's why we don't talk about deceleration, because if we said that this car is decelerating here, then as it goes backwards, it's like, well, now is it accelerating backwards? But the value for the acceleration never changed. So that's why we sort of only have one term. Now let me ask you another question. If this is the positive x direction, or if this is the positive direction, what would you say the acceleration of this car is positive or negative? The top one? All right, this one has a positive acceleration. The magnitude of A, or I guess just right, the direction of A is to the right. What about this car? This one is negative, so the direction of the acceleration is to the left. And like I said, if I drew these arrows the right size, it's a constant acceleration. Right? The acceleration doesn't change. So in physics, we never say decelerate. What we do is we talk about the direction of acceleration. So throughout the entire path of this car, the acceleration is always to the left. So that means that this car starts off going fast, and since the acceleration is pointed in the opposite direction to the velocity vector, the car is going to slow down. Once it stops, then the acceleration vector still wants it to accelerate to the left. Now the acceleration vector is pointing in the same direction as the velocity vector, so it speeds up. Okay, so to sort of summarize, when we have acceleration in the same direction, oh no, I hate when that happens. All right. When we have acceleration in the same direction as velocity, we say that the object is speeding up. All right. When the acceleration is in the opposite direction, oh, that's not the right color. Let's try that one. When the acceleration is in the opposite direction, now we have an object that is slowing down. Okay? Does that make sense? Is that okay with everybody? All right, good. All right, so let's make it just a tad bit more complicated. Now I realize that we're talking about motion in 1D to start off with, right? But I do want to break out and go into 2D really quickly. So let's ask the question, when you have an object that is moving like so. Nope. This is point, we'll call it point P and point Q, and the object is making a circular path. It's kind of a bad. All right, so the object now, be it a car or whatever, it's kind of a funny circle. All right, is going in a circle. All right, but the important thing is that at point P, the velocity is, let's just assume this is a car, 30 meters per second to the east. At point Q, the velocity is 30 meters per second north. All right, so the magnitude of the velocity is the same. So is this car accelerating? Mm-hmm. Why? Why? All right, exactly. So velocity is a vector. It has a magnitude and a direction. If either one of those two things is changing, then the velocity is changing. So this car's velocity is changing even though the magnitude isn't. If the velocity is changing, that means the acceleration, there is an acceleration. A is non-zero. Okay? So yes, this car is in fact accelerating. Can you tell me what the direction of the acceleration is? Counterclockwise. That's a good guess. It's not counterclockwise though. Let me ask you, let me be more specific. What is the direction of the acceleration at point P?
Northwest.
It's not northwest? It's not east. If it was east, then the car would speed up in the eastward direction, right? It's not tangent to the curve. If it was tangent to the curve, then it'd be east down here. Yeah. Out. As in like towards out of the board. You guys have to tell me that that's really hard to see. Into the board? Sure. It's not into the board. It's not out of the board. It's not northwest. It's not east. We're running out of options. It's north. It is north. So somebody said north before. Yes, so it's perpendicular to the velocity. Okay, this is not really all that obvious, but if you take a minute and think about what's happening here, the acceleration causes a car to speed up, or slow down, I guess, all right, in the direction of the acceleration. So at point P, the car has no motion in the north direction, right? The car it's moving eastward. No motion in the northwards direction. But we want it to turn, so we want it to have some motion in the northward direction. So we want the acceleration to be northward. Okay? Now, since we don't change the magnitude of the velocity at all, that means that there's no component of the acceleration in the direction of the velocity. Because I just said it right up here. If we have an acceleration that is either parallel or anti-parallel to the velocity vector, that means the car's got to speed up or slow down. But but think about vectors, right? If I have an acceleration, let's draw it like this. If my acceleration is like so, well, if I broke this up into its vector components, well, now I've got an acceleration that's parallel to the vector velocity, which means that the car's got to speed up or slow down. So the only way that my acceleration can be oriented so that the speed doesn't change is if it's perpendicular to the velocity vector. All right? So anytime, if I say that another way, anytime the acceleration is perpendicular to the velocity, the speed doesn't change, only the direction changes. Okay? So if A is perpendicular to V, only the direction changes. All right. For completeness, if A is parallel to V, only the speed changes, or the magnitude of the velocity changes. Okay? That only leaves the possibility that A is neither perpendicular or parallel, neither perpendicular nor parallel. That means they both change. All right? So if A is somewhere in between, then the speed and the direction have to change.